Okay, hello everybody. Welcome to one more Hel.A.S Colloquium. Today's speaker is Professor Christophe Sauty from the Observatoire de Paris in France. Christophe did his PhD back in '93 in University Paris 7, and the topic of his PhD thesis was on Mhd studies of winds and jets, and particularly the effect, the effect of anisotropy in mass Mhd flows. Christophe is currently doing his research at the LUPM, Laboratoire de l'Univers et Particules de Montpellier of the University of Montpellier in France. He is a worldwide expert in mostly analytical Mhd work on the winds and jets around various stellar objects, including young stars of Tauri stars, as well as supermassive black holes in AGNs. Christophe is really having extremely strong ties with the Hellenic astronomical community. First of all, he did his PhD under the supervision of Canaris Zinganos. He is an active member of Hel.A.S since '97. So today's, he's also very fluent in Greek. So today's seminar from Christophe, it's on jets from young stellar objects and AGNs, from analytical models to simulations going into microphysics. So please go ahead, Christophe. The floor is yours.
Λοιπόν, σας ευχαριστώ πολύ που με καλέσατε και θα συνεχίζω στα αγγλικά βέβαια. So, okay, I hope I'm not too ambitious. I wanted to show you a few results, more or less recent on jets that we are working on. And here is the list of the collaborators that have been participating in those results I will show you. So there are a lot of people, I cannot show all of them. So in Athens, but also in Porto and Montpellier, and of course, Paris Observatory, and also in Turin. So, okay, I will focus on jets on two kinds of objects. One are young stars, and more specifically, Tauri stars, as you know. So these objects have an accretion disk. You see here in the midplane, and from this disk, there are material flowing out, which is collimated into jets there, more or less perpendicularly. And of course, this is an interplay of magnetic field and matter and gravity that explain all that. And these jets, there are a lot of shocks or turbulence moving in, so kind of instability. But first of all, there is the problem of the formation of those jets. And one issue is to understand why they are so complex objects. Here is, so RY tau will be my fiducial object for YSOs, and we're trying to model this object precisely. And you see here a multi-component image where you clearly see the accretion disk around the star and the jets that propagates on several AUs and hundreds of AUs. So there is a relativistic counterpart. I'm not going to talk about all kinds of objects. My focus will be on extragalactic jets from active galactic nuclei, where you have an accretion disk. I didn't show images of this disk, but this is about the same. And there is a strong jet here, more or less powerful, finishing with hotspots in FR2 object or lobes in FR1 objects. And also there the plasma is accelerated to very high velocities. And here, in fact, you see that the internal shocks in the jets are moving at apparent superluminic speed, which just means that they are very relativistic. And you have to explain also in this object the acceleration. Of course, my typical favorite AGN jet is M87, which is well known for a long time. I didn't show there, but there are observations in all wavelengths from radio here up to gamma rays right now. And in those all jets, you have a jet at kiloparsec scale, and inside inner parsec scale jets. And the amazing thing is that now we have images of the central black hole and the environment of the black hole that is in M87, as you know. So one issue, of course, for YSOs, it's a long-standing problem, but this is also true for AGNs. So in YSOs, you know that there are various classes of objects from class 0 to class 3, and I will focus on class 2 object where you have classical Theta stars, where you have the accretion disk and the wind that collimates into a jet. And of course, one issue is how do we remove angular momentum? One, to have accretion processing onto the star, but also to explain why the stars are moving and rotating so slowly, and how they remove angular momentum, because if you add the material from the disk, the first idea is that you should increase the angular momentum. So the second question on those objects is also the fact that there are multi-components. In other words, okay, I have a problem to, okay, it's moving again. So the star is here, the accretion disk is in the equatorial plane, and out of the disk, you have a disk wind that flows out, and some of the material is accreted onto the stars. And this is what I will call the magnetosphere of the star here, where you have part of the material of the disk that is going in and falls onto the star. Of course, there is a stellar wind out of the star, which is a component that I've been studying quite a lot, because most people focus on the disk wind and on the interface between the magnetosphere and the disk wind, where we have supposedly conical winds or X winds, which I will prefer to call magnetospheric ejection. And you see that basically there are at least 2, 3, or even more components in the jet, because there's some part of the material that flows out from the star, some from the disk, and apart from the interface. And I'm not even talking about the molecular flows that are flowing outside, but which I will not discuss here. And if you look at AGNs, you have the same kind of problem. First, you have a matter of inclinations that you've seen in the previous images, where, of course, if the jet is coming towards you, there is a relativistic beaming. But also the question that some objects do have jets, like blazars and quasars, radio-loud quasars and radio galaxies. And on the other side, you also have radio quasars and Seyfert galaxies that do not have jets. But even there is also the question that part of the beam may originate from the black hole itself, or above the black hole, and or in the black hole magnetosphere or from the disk that is around it. So again, you have a multi-component jet. So you have to solve for the Mhd equations, and I thought of not showing at all any equations during this talk, but after all, I thought, okay, this is a bit cheating, even if you don't like equations. The point is that in order to understand something here, we have to solve some equations. So I will not go into the details, but these are the well-known Mhd equations. And on the left, these are the equations that you have in the non-relativistic case, so especially for YSOs. And on the right, I just make a summary of the axisymmetric, steady, and ideal 3+1 Mhd equation we use in a Kerr geometry. So we're not going to do fully relativistic stuff. It's just at most in Kerr metrics. And you can recognize similar equations as there. Okay, I think in terms of equations, that's almost all what I will show. So the first way of dealing with those equations, especially in the steady state, which is in principle should be easier. Finally, it's not that easy because all simulations, so big codes, Mhd codes, are usually dealing with the time-dependent equations because it's easier in terms of boundaries. Because if you go to the steady states, you have to deal with multiple critical points, which makes your life very tough. So I'm not going into the details of those models, but basically there are two kinds of self-similar models. One will be the Disquin, and starting with Blanford and Payne, that you know, where everything scales with the radius, because there is no intrinsic scale. So everything scales with the power law of the distance from the central object, but this distance can be measured also in terms of magnetic flux. So alpha, all the alphas here are dimensionless magnetic flux. And the other one is stellar outflows, where so that we will apply also to the atmosphere of black holes, where instead of scaling with the radius, we scale with the co-latitude. So starting from the axis of the object, everything is axis symmetric. There is still rotation, so it's 2.5 dimensions, sort of. But this makes our lives a bit easier. So I will just show you two examples of what we have been doing. So one was to produce a, okay, sorry, there is the D missing here. One Blanford and Payne Disquin type of solutions, and with Nectarius. And the thing was that for the first time, we really had the solution. So the flow, the disk wind here are those lines here in the poloidal plane. So get used to that, because that will be the main representation. I will show you the vertical axis here is the polar axis. So the axis of the jet. On the equatorial, the x-axis, you have, in fact, the equatorial plane. So the disk is in the equatorial plane, and the disk will be always the source of material, but we will not deal with the inner part of the disk mostly. And the difficulty here is that there are some kinds of horizons, in the sense that they are Mhd horizons, which are exactly like the horizon in the relativity, and you have to cross those horizons in terms of causality. But there are also regions like this one, which is not the horizon, but it is the ergosphere. So regions where you are moving from the equations are moving from elliptic to hyperbolic, which makes things very complicated. So the originality of this wind solution here that is collimating, or more or less focusing onto the axis at the end, is that it is crossing all three critical points: the slow mode, the alpha mode, and the fast mode. In parallel, we had some solutions. I've been studying that since my PhD, of those meridional self-similar solutions, where you have here solutions for the star itself. So here is my best solution, sort of, that we were applying to our white Tau stellar jet. So the microjet in our white Tau, and fits with this solution really fits all the observations at that time. And you have the star here. You have the jet coming from the star in pink. Okay, here is the full image. So you really have the star. The green lines here are the wind, this wind coming out from the disk, but the disk here is not really realistic. So the solution is not really valid. And what you have here is not really physical in our solutions, but this is the region where you expect to have the magnetospheric accretion with the material coming from the equatorial plane, from the disk, and falling onto the star here. So most of the representation, like the one on the left, this is only one quadrant, as you see here, okay? So again, this is the polar axis, and this is the equatorial plane. And because of the symmetries, this is bipolar, this is axis symmetric, so we show only one quadrant, which such that we save some space. So I hope this is obvious for all of you. So as I said, you have to cross those critical points, and this is the most difficult thing to do. And here it's another example where we have an extension of the meridional self-similar models, but in the case of general relativity. And there, the idea is to model the spine jets in around black holes, where you have, okay, I don't know what happened, but it seems that the surface have been stretched, and it is not looking very nice now. So, but basically the idea is that you have photons or any radiation field here that will create some pair, and the pair creation will can explain the jet by the Blandford-Snijek mechanism, where some of the pairs are falling into the black hole. So here is the inflow, and there is the outflow. So in fact, the inflow and the outflow, both of them have to cross from the stagnation surface. They have to cross the three critical points again. So one of the, we have been developing those stellar jet for a long time, and one of the last results are here. So that was the PhD of Loïc Chantry, and I can show you. So if you remember this theta solution, you see that you have something that looks very similar. Okay, you have the black hole here. You have a zoom in this inner region, which is on the right, where you have the black hole. Here is the ergosphere of the black hole. And you see that the blue region here is material falling in, and in the model, you have some stagnation surface here where pairs are created. Of course, there are other models of that kind, and there are a lot of works done by Levinson, for instance, and Nathanael and Kodopoulos, as you know, dealing with mostly Poynting flux dominated flows, while here material is really important. So our idea was not to reproduce the results, but to give an alternative where you have a lot of material, and here the corona is very hot and very high temperature, so you are far from a purely force-free or Poynting flux dominated flow. But nevertheless, these solutions, because of the outflow here that at large distance converge and collimates into a jet on large distances, the idea is that you still have a way to remove not energy. We didn't find solutions that really extract energy from the black hole, but that do extract angular momentum from the black hole and slowing down the black hole. So this is quite efficient, and this is quite promising. In fact, there are extension of the models to have not only pair creation on a slide, but on surface and just layer, but we could have pair production on some zone, and we will work on that later on probably. In order to avoid to have too many slides, I did not show, but Loic has been working a lot also on the coordinates you're using to show that if you use conformal coordinates, you can really show that in reality the magnetic field lines are anchored onto the black hole perpendicularly, because the classical Boyer-Lindquist coordinates do not show the real angles, because you have to imagine that although this is in the poloidal plane, okay, so again, this is the polar axis, the equatorial plane, and everything is rotating, including here the matrix, because you have a Kerr black hole, so everything's rotating. So in fact, the real picture would be in 3D. And because of the frame dragging, in fact, you don't see the angles very correctly. Why do I insist on that? Is just because, in fact, it means that when you make the drawing with the right angles, you see that the lines are more flaring. So there is a more efficient magnetocentrifugal driving. And although we do not have the proof here, but I do think that that could explain why relativistic jet can be launched even if the angle does not is not the famous 60 degrees from the Blanford and Payne model. Okay. Enough with the analytical works. So the idea was to present you those semi-analytical solutions that we have. And the idea is that they can be used as boundary or initial conditions to solve the Mhd equations in a code and to explore them in simulations. So I'm back with the Mhd equations. Here I show you only in the non-relativistic regime to make it simpler. Just one thing is that the last equations here, so after the divergence, the magnetic flux conservation, the mass conservation, the Faraday equations for induction, and then the Euler equations, you also have the energy equations, where usually everybody uses some kind of polytropic equation of states. I didn't write here, but we have also a generalized equation of state, which is the Taub equation in case you have relativistic temperatures. But what you don't say when you have a polytropic index gamma that is not 5/3, so which is not the adiabatic one, in fact, it amounts to hide somehow some heating. And here gamma is 5/3 for monoatomic gas, and small gamma is the polytropic index, and it's smaller than big gamma. And you see that that means that you have some heating there. So this is the case for disk wind models like Blanford and Penn and all the rest. And this was not the case of the meridional self-similar, where the heating was an output of the dynamics. So the idea in the simulations and the more recent simulations we are doing is to try to, instead of using a polytropic equation of state, to have a code that can adapt to various sources of heating. So starting with the analytical solutions with the analytical heating, but maybe hopefully moving to more realistic sources of heating with the same code. So the first, and this is the big work done by Titos Matsakos, during his PhD, but there are two papers I will mention because we are using some of the methods that he has developed there. One in 2009 was showing the propagation of the self-similar solutions at long distances, and for the first time mixing the stellar jet with the disk wind. Okay, but you don't have the disk or the star there. This is far below. You just mix the two at some distances, and you look how this propagates into the interstellar medium. And the idea was that by a slow variation of the star flux, mass flux, of 10 to 20 years, between 10 and 100 years, 10 on the above and 100 years here. So just by varying the stellar jet mass flux, you see that in fact it will affect the whole disk wind, because it will create nodes, it will create shocks. And the funny thing is that although the shock, the stellar jet here is very weak, also because it's polytropic, so adiabatic, so it's very weak. Nevertheless, it affects the disk wind, and the shock, the radius is almost 10 times the radius of the stellar jet. So you see that my idea is that you cannot really neglect the effect of the stellar jet, even if the stellar jet is very weak compared to the disk wind. That was the first result out of that. The other one here was that you see that those nodes that looks like HH objects are very well spaced, like in HH30 and HH34, and that they can be explained only by the activity of the star itself, because 10 to 100 years is exactly what you expect from the cycle of the central star. With Titos, we also have been studying non-symmetric jets. So I'm not going into the details of those, but in 2012, this is again the propagation of a mix between the disk wind and the stellar jet. The mixture was a bit different, and I just wanted to mention that because we are also using this in more recent simulations. Of course, this multi-component jet would be studied in the relativistic case. So I've been working with those simulations are done both with IMR VAC, and they are quite different. And so the fact that they are relativistic, of course, is because you have to deal with the relativistic Mhd equations for AGNs, and because we know now that the fact that the inner jet is highly relativistic will stabilize the whole system and will prevent from some of the instabilities you see in non-relativistic jets. Okay, both publications, in fact, were trying to explain the dichotomy between FR1 and FR2 objects that we had inferred in the analytical work, related to the fact that the ambient medium is more or less dense. We know that in FR2, the jet is very powerful and the ambient medium is relatively poor. And when you play with these multi-component jets, you again have that. And again, in those simulations, you have three components. You have the outside medium, but you also have the inner spine jet and the disk wheel. But those simulations were using ad hoc conditions at the base. And currently, the idea is to, so Loïc Chantry is in doing a postdoc in Turin, and we are still in contact to work with the people in Turin on and also with Canaris is involved in there to work on jets. So there, the idea was to use at least the spine jet, the analytical solution, to deal with the spine jet instead of starting with ad hoc conditions. So Loïc did put a lot of efforts to have, at least in the boundary conditions, a solution that is already in equilibrium, which is not the case if you take ad hoc conditions without taking care of the equation. That means that the Graf-Shafarov equation here at the base of the simulation is solved. And of course, you have the classical, okay, maybe this is a bit small, but you have the bow shock. On the left, you have traces only in the inner spine jet, okay, and on the right, you have exactly the same simulation, but the tracers are in the disk wind, sort of. So these are relativistic simulations that are more or less in the continuity of what Titus Matsako did for YSOs, but now applying to the case of AGN jets. And of course, you have a cocoon and you see a lot of structures ahead and a lot of instabilities like what you see usually. What I found amazing compared to other simulations, of course, to show you, the results might not look very nice because it's so simple, but I found quite impressive the fact that if you make a long time run, you see that, okay, here the simulations is finished, but you could follow it, it would be exactly the same. You see that the jet inside here, if you look a bit before, oops, I don't know if, okay. You see here, this is not moving at all, so it's completely steady. So what I find very fine at the end is that if you let time grow, you see that the jet becomes completely steady and you get a completely steady solution. And there is no more instability there. Of course, there are some features that are unstable, which is the connection between the outer medium, which was force-free at the beginning. So they take care to have a force-free solution outside, completely analytical, but the exact solution. And you propagate there the solutions there. which has 3 regions. So that's just an example of the vertical component of the velocity. Beta sub z is just the v over c along the axis. Okay, here is the inner final state of the inner jets, so the spine jets here, surrounded by the an outer layer of the same jets here, so that you can see the structure. So this is the previous simulations, and you see that at the boundary, so there at the bottom, you have 3 regions. You have the spine jets with very high velocity, mildly relativistic D-squint, and the connection with the outer medium. I'm not showing you all of that. This is work in progress, but you see how it is interesting to start with exact solutions, at least on the boundaries, because this can affect the stability of the whole structure. So you see that we have quite a lot of results with the propagation of the jets. We are also working on making models for the inner part of the jet, and this is again, this is our Y tau, where we use the stellar solution, and just by reversing the flow and increasing the density there, we could have nice simulations where you have a D-squint, but there the D-squint is not even, well, it is Keplerian because we forced to have Keplerian velocity, but this is not the D-squint, the Blanford and Penn D-squint. That's another work I hope I have time to show you. This was just to model the inner accretion and jet connection there, because most simulations are, first of all, I just discovered that most simulations, in fact, have a small box. Here, you can't see that, but the simulation really goes up to 25 AUs. So here you see you are 1/10 of AU, but the real simulation goes up to 200 times that. I mean, so 25 AU out. And you see that the amazing thing is that the stellar jet is remarkably stable in those solutions. Also, the accretion, the magnetospheric accretion is very nice too. And you see there in terms of mass flux that, of course, there is more mass flux going from in the accretion than the mass loss rate there. And you also see that between the left solution and the right solutions. So on the left top, you have the density. On the bottom, you have the mass flux. On the right, you have a higher accretion rate, so higher density here. So this is again the map of the density. And here below, it's the mass flux. The arrows are the velocities, and the white lines are the magnetic field, and everything is in the poloidal plane, again, with the polar axis here and the equatorial plane here. And what the amazing thing is that most simulations do show, will show you that there is a strong magnetospheric ejection, because they do not take into account stellar jet. But you see that if the stellar jet is not too weak, and this is a relatively realistic one, because this is the one that corresponds to the microjet of our Y tau that we modeled with the analytical solution. The analytical solution is stable, and you see that it prevents, if the accretion rate is not too high, it prevents from having coronal mass ejection, sort of. This is the same kind of solutions evolving with time. So you see more clearly that on the right side, you have this ejection that goes away. And like most simulations, I'm thinking about Zani and Ferrara solution. For instance, the mass loss rate here is about the same as the mass loss rate from the star. So typically 3×10⁻⁹ solar mass per year, which is what we expect. And in fact, the accretion rate here is simply twice the accretion rate that you have here. So a factor of 2 is well below the precision of the measurement. So observationally, you would not be able to distinguish between magnetospheric accretion of this one and this one. That both would be exactly the same. You see that clearly there is so the disk here stops here. There is this kind of static zone here. And this is the accretion flow. So that's the accretion funnels there and the stellar jet. You see in the solutions that everything is remarkably stable, completely steady. Of course, there are some slight motion here, but they are just periodical. And basically, this is completely empty. What happens in the meantime is that Petrov, in several papers, have shown that our YSOs shows two states in terms of luminosity, a quiescent state and an active state. And this would correspond exactly to that, because here the magnetospheric ejection would sweep out the disk wind material, clear up, and making the star visible. While here, the absence of magnetospheric ejection would not sweep out the material, and you would have a lower stellar luminosity. So this model can really explain the two states you have here. Of course, in the now we want to adapt our model to mix both the stellar jet solution with the disk wind solution, starting with the stellar solution we were using in the previous simulations to the 211 paper and the 2000 paper by Nectarius of the disk wind, mix the two. And how do we mix the solutions? Well, in fact, we do have the way of mixing that was developed by Titos Matsakos in 2009. And so this is the one, and another one in more sophisticated in 2012. So far, yes, we have solutions. The solutions I will show you are with the first mixing, but we do have at least two ways of mixing the solutions, which basically is making that the weight of the stellar jet is dominant inside. Okay, in fact, we even skip the inner jet as the stellar jet, and progressively there is a weight, and the weight of the stellar component decreases, the weight of the this component increases up to 1, and then at the end only the disk wind remains. However, there are some subtleties, because if you want to keep divergence of B equals to 0, you have to do the weight on the flux, the magnetic flux, but then you have to recalculate sort of the magnetic field, and also to adapt the velocities such that it is, if it's ideal MHD, the poloidal velocity should be parallel to the poloidal magnetic field. So we take care of that. So the process is quite long. This is what the mixing looks like at the beginning. So you have the stellar jet there, you have the disk wind there, and you have some in between, which is mixing the two. This is really recent work done by Shadi Meskini, who started a PhD this year with us in Montpellier. So we are just at the beginning, but we already have some solutions that are interesting, although the disk wind suffers a lot of problems at large distances. and it is almost squeezed, as you can see. So this is after some run. But what's amazing is, nevertheless, there is still a stellar jet there, and very close to, okay, these solutions, the accretion disk is quite powerful, and in fact, there is a huge region of accretion there that you can see on the left, like here at the bottom. Its material goes up and then down and falls onto the disk, but then ultimately will finish on the star. Nevertheless, you still have some stellar components, and these are at various times. So it was time 25, 100, and 200, which means, if I remember correctly, one stellar rotation is 3 point something. So you see that 100, 200 is almost 100, well, a bit less than 100 the stellar rotation. So it's quite a lot. And if you look at the inner jet, this is very, very similar. And so you see that it seems to be very stable, and that's amazing. Of course, in this solution, but remember that you never saw, in publications, you never saw what the jet looks like at long distances. By the way, the group of Romanova never talk about jets. They talk about conical winds, for instance. So, and you see here that at large distance, the stellar jet for the moment is a bit weak. No, sorry, this was another solution. So the solution looks like that. I forgot to put them on the slides, but in fact it is a bit decreasing here. So the disk wind is also squeezed towards the equator on later stage, and but okay, this is quite promising. If you make a weaker disk wind, you have the solutions after sometimes 25 here, where you still have the magnetospheric accretion. So that's amazing how this inner part really looks very similar to what the original stellar simulations were. So with the stellar jet here and the accretion here and the weak disk here. Of course, on large distances, this one, it looks like everything is destroyed. Okay, we should have plots with another scale here, but you would probably see more details. But nevertheless, you see here that the stellar jet sort of whipping out everything. Okay, the point here is that the heating in these solutions was the stellar heating, so it was very strong in the middle. And of course, we have to study what happens if you put stronger heating in the disk wind. But you see that it looks like probably completely adiabatic disk wind cannot survive, and you need to feed the disk itself with some heating, with some corona, for it to survive on large times. Again, this is the weaker disk solution, and you see between time 20 and 25 that the solutions are very similar, with this kind of funnel here, which reminds me of the conical winds in Romanova and collaborators, which is quite similar. I'm almost done. I would probably not have time to go into the details, but in parallel to that, we start also a PhD, that's the PhD of Valentin Brun, with Alexandre Markovit again in Montpellier, where instead of studying now the jet itself, although it might have some applications for the jet, but we are looking inside the disk. Okay, you have a kind of hydrostatic disk with the vertical equilibrium, the hydrostatic vertical equilibrium here. The star is on the left. Again, it's 40 Tauris. And the idea is that you have hydrogen, but because of the temperature, because of X-rays from the star or flares that are above, you have a complex structure with a complex chemistry where you start completely ionized with H+, but then you move to a region where you have H, which is dominating, and then H2, the molecule H2. I mean, well, you know, the astrophysicists have a bizarre way of denominating that's the molecule H sub 2, I mean, inside, and also some kind of helium everywhere. And the idea is that you have a flare just above the disk, and you look how this flare, which has some temperature here, and this is the spectrum of the thermal particles, but the flare creates non-thermal particles, and we look at how those non-thermal particles that you inject will propagate into the disk along the magnetic field line. So we are studying various magnetic field lines, vertical or parabolic. So this one is like in the disk wind, but if there were some kind of dead zone inside the disk, the accretion disk, maybe the magnetic field line would look like that because there is more inflow, more accretion on the outer part of the disk. And also there might be variation on the toroidal magnetic field. So we also studied these. I'm not going into the details so far, but just to say that this is quite promising because very close to the disk, we don't really know if it's completely ionized. But it seems that if you have flares, so far we are looking only to strong flares from 1 million to 100 million Kelvin, but the idea is that those non-thermal particles that are very energetic propagates into the disk. And here you see that this is in the orange is the injection spectrum. And you see that how the spectrum evolves. So of course there are losses, and how the spectrum evolves as you move inside the disk. So this is with increasing column density. And the point is that with the increasing column density, you see that you still have very strong ionization rates. Of course, this is for one event. You have to average over several events, and everything is moving. So maybe the conclusions is not secure for the moment, but the idea is that it's a very good way to ionize the inner disk and to heat also, and probably heat also the disk wind. So the idea is at the end of the day to have rates to how we can heat the disk and the outer disk wind. And as conclusions, I would say that I hope I've shown you that I think we have stability of self-similar solutions, that the idea is in the simulations to, well, what happened? Okay, is to have to study different sources of heating in the wind, and of course try to start with self-similar solution even inside the disk component, and on the longer term run, once we know about the propagation of relativistic jets, also to apply that to the inner structure and make simulations of the inner part of the relativistic jet. I think I'm done. Thank you.
Thank you very much, Christophe. So now time for discussion, questions. So please raise your hand so that we start the discussion. Nikki Lafis.
Thank you, Christophe, for this nice overview of the work that you have done. You said young stellar objects and AGN. Is there any reason why you do not address at all the jets from stellar mass black holes in X-ray binaries?
Yeah, there are plenty of good reasons why, because you cannot, in one life, you cannot do everything. Another is that I think there are a lot of people that are doing a very nice talk on that. And okay, that's not a good reason, because you're right that somehow it is, we could in principle try to apply that to those objects, but as far as I know, we do not have observational constraints as good as we do have with M87 and objects like Hawaii Tau. So basically that's a reason why so far we concentrate on those objects, because we do have a lot of information on that to constrain the parameters. And a problem of those models that you've seen is that there are so many parameters that you need maximum information to have to be able to start doing something that is physical. But there is no reason like, I do believe that maybe that at least this method could be applied also to stellar mass, to galactic, how do you say that, stellar mass objects or black holes. Yeah, definitely.
Okay. Don't you expect then things to scale with the mass of the central black hole, and the jet then should behave in a more or less similar way, but scaled way? So
I'm not so sure, because if you look at what people are, a lot of people trying to insist on the analogy between the two. But there is always something hidden below the carpet if you look very carefully, because it never scales down exactly like the mass of the black hole. There are always at least one other parameter you need to fit. So that's one thing. The other thing is that lots of models for binaries where there is this episodes where the inner disk disappear and there is a strong corona. And maybe it's exactly the same, okay? Maybe not. So I would like, I hope that at least what we are doing now could apply somehow to other objects and to galactic black holes, definitely, to stellar mass black holes, but I would be cautious anyway.
Okay, thank you.
Okay, now let's move to Konstantinos Gouliatos.
Yes, Christophe, thank you very much for the very nice talk. I enjoyed it a lot. What I wanted to ask you is that you had a model of a jet simulation with an injected jet, where actually there was a spine, and then at some point the jet seems to become much wider and open. I don't know if you can go to this slide. Is this some kind of instability that you see there, or the confinement instability or something like that? Because we were getting very similar results with Sergei Komisarov when we were simulating not jet injection simulations, but steady equilibrium solutions, and then we let them to evolve.
Okay, I was expecting, so normally you should see my screen, okay?
Yes, yes, I can see your screen.
Okay, yeah. So are you talking about those simulations or these ones?
Not these ones, the ones, yes, these ones.
Okay. No, here we are not expecting to have something completely different from the others. And that's why I showed you the previous one, which were done with the IMRVAC. I know your work. I mean, we do have some instabilities at the head of the jet. And you also have this cocoon that is forming, and I guess this is not very different from what you got. But what I find amazing is that once you run the simulations long enough and you let those instability go forward, and of course they can be physical. I mean, probably they can explain the large distance jet. But what I find very nice, which I didn't see in other simulations so far, is that the spine jet here becomes completely constant, uniform, no completely stable. And the funny thing is that the disk wind, except those things that are in the intergalactic medium, the disk wind somehow also becomes completely steady. And these are very recent results, okay? So I don't know, but these look, okay, everything above at the head there looks to me more classical, what most simulations show with the instability, and I guess for this is nothing new. But do you have really this stable thing here?
Yes, well, actually we have the stable thing, but we have it up to the so-called reconfinement point. It doesn't go beyond some distance, so we have it up to the reconfinement point. So I'm just trying to think if the injection simulation is going to give something fundamentally different from the equilibrium simulation, and it seems that there is something interesting going on here.
Yeah, I think, okay, okay, I'm a bit short in explaining those because the results are Lloyd gave them to me 2 days ago, so they are very recent simulations, and I was not I'm not leading anything in this. I mean, that the colleagues in Torino that are really working on that with Loic. So, but yes, I think it's interesting. But okay, maybe okay, I should have looked more precisely on the simulation you're talking. Maybe your simulations were also starting much closer from the disk, no?
Yes, actually the simulations were starting from an equilibrium and we were not injecting anything, and then we had already formed the jet. So probably this is the difference.
Yeah, and I will look at those. Well, I will look at the simulations, but my idea was that you were really dealing with something we have not attacked yet, which was the formation of the jet itself from the disk, so very close to the base.
Yeah.
While those simulations are to be compared not to the work I've shown you on the inner stellar jet, but more on the work that was done by Titos on the propagation of the jet. There we are really far above the Alpine surface. I mean, we are really in the super fast region.
Yeah. Okay, thank you very much.
Okay, thank you. Other questions, hands? Not yet. So I just have a short question. You showed to us some discussion about the determination of the heating term QH. This looks like to me like an effective heating term. So so can you comment on what physical mechanism is doing this heating? Is it viscous, ohmic heating? What is?
I'm glad that Canaris is there because this is a very long fighting issue. And I didn't start it. I mean, Canaris was the first to have to fight with that. What I was pointing is that so far, I think there is no model that have a realistic equation of for the energy. So one is what we did with the spine jet or stellar jet, which is to calculate the heating a posteriori. and give it as a boundary, but taking care that probably observations will fit with what we do, which is the case for our Tau. I mean, we check that the temperature profile we have are realistic, and although people will claim that there is no stellar jet in T-Tau, the point is our Tau is a very good example because there is an extended X-ray region inside, which means that there must be some corona that's up to 1 million degree inside the jet. So there is a stellar jet, and it's not negligible. But okay, I agree. This heating is somehow ad hoc, and we cannot. But the point is that when people use the polytropic equation of state, this was shown by Titus Matsakos in the first paper. And that was the equation I was showing, is that even if you use a polytropic equation of state like that, but gamma is not the adiabatic index, you are lying, because somehow that means you put some heating. Mm-hmm. So the idea was that when we do the mixing between the disk wind and the stellar wind, instead of putting an equation of state like the polytropic equation of state, we calculate everywhere the small q, and we inject the heating, we make a map of the heating, okay? So far, the heating we put is the heating that are the heating sources that are given by each analytical solution. But the good point is that in doing so, that means in the future, we can, once we really understand with those sources of heating what's going on, we can replace those heating sources very easily by other sources of heating, or add other sources of heating to study what can be the effect, for instance, of the last part I was showing, what are the effect of flares and energetic particles that are coming out of flares. Just on top of that, with exactly the same simulations. And I think that the advantage of those simulations, the flexibility that they offer. Because you're right, that's one of the major issues is so far in none of those objects, we have a clear idea of the sources of heating, at least very close to the central object, okay? I'm not talking about far distances where things are a bit more safe and probably easier to understand.
Thank you.
There are a lot of people here working on the solar wind, and they know what I mean, because solar wind is a very good example of complicated system on that respect.
Okay, other questions, comments?
I don't know if Canis wants to talk. No.
Yes, I can.
Okay.
I can. Spiro, can I ask something?
Oh yes, of course, yes.
Yes. Okay. Ευχαριστούμε, Christophe. You succeeded to give us the flavor of so many problems, like the analogy of young stellar objects and AGNs, the heating and the energetics and the dynamics of the flows, and the stability of the flows, and also the simulations. This is a complicated problem indeed, and you have been working on that together with other collaborators for several decades. But there are several interesting conclusions which have been outlined in your talk. For example, it's amazing to me that there is a complete analogy between non-relativistic outflows and general relativistic MHD outflows. This is it's not a priori expected, but the same methods can be carried out between those two cases. The heating, of course, in these simulations, it's done a posteriori, as you pointed out. But excuse me, it would be interesting someone to focus on the heating for the particular models. Now, my main question has to do with stability. There are a few, very few approaches on the stability, and some of them are done here at the University of Athens with Nectarius student Sinis. But it will be interesting to see if the jet is stable or not. I mean, of course, we observe jets, and they therefore should be stable. But taking these solutions and putting them as initial conditions in the stability examination, do you think that it would be a way to say something about the stability of the system, either in the general relativistic Mhd example or in the non-relativistic Mhd example? Because the stability is something we see, we see in AGNs, in some cases, the strong jets, which means they are stable. Sometimes we have weak jets, which means they would not be stable. So this is one of the many questions one can think of after seeing your general outline of the problems that can be addressed, starting with the simple model of self-similar outflows, relativistic or non-relativistic.
Yeah, I agree. I think that's already what we see here, which is amazing, is the extremely stability of the self-similar solutions. So we discussed about the fact that here we had an equilibrium, and also what we just discussed before, as it's not the only case where you are starting with an equilibrium, really have something stable. I think those simulations that we're done with people in Porto here also shows, you see that this is extremely stable inside. This is the purely analytical solution. And we had already explore the discrete solutions also, they are very stable. So of course, where you change on the boundaries where you have lots of change, it changes. Here I think it's too preliminary, but I guess because so far we are struggling with what heating we do put, how the disk should be compared to the star. But even in this simulation, I found the fact that the stellar jet is still there, like it was still there in the Titos simulations of the propagation. The case that the relativistic jets are very stable indicates that not only self-similar solutions seems to be stable. If you remember, a long time ago, Jean Everts was arguing that, okay, your solutions are very nice, but I'm pretty sure that the day you will put your solution in a box and run simulations, the simulation will destroy the self-similar solutions. And it turns out this is not what we see so far. Of course, you have to be very careful about the heating sources you put, because this is the crucial points. The heating you put inside. But as long as you are close to something that coincides with the analytical solutions, apparently you get something that is very stable. But of course, you're right, it could be nice to study, especially, we started discussion about that some time ago with Veronique, you remember, Canaris, about what kind of instability we do have here. Is it Rayleigh-Taylor? Is it Kelvin-Helmholtz? Is it a mix of the two? And of course, a general analysis of the Mhd instabilities there would be quite interesting. But as a matter of fact, I'm now more and more convinced that self-similar solutions are very stable.
Okay, that's interesting.
Yeah, and that's an advantage compared to a lot of simulations that when you start from equilibrium, but Yorgos just said the same, basically, when you start from an equilibrium, you reach, yeah, I didn't discuss that because I didn't have time, but as a matter of fact, these simulations get stable, not necessarily steady, but stable after 3 stellar rotation. I know that nowadays there are simulations doing that, but the most famous simulations in the past, they were taking 10 times more. I mean, decades of rotation of the central object to reach steady state. The fact that you start with already something that is close to equilibrium makes your life much simpler. But also it tells you that when you start from initial condition, you should not think of that as an evolution of the system. I think it's a bit dangerous to think that what you have here is the evolution of the stellar wind or whatever. What you do have is a relaxation method, but not only in our simulations, in all simulations, basically. Even if you start with ad hoc solutions, you don't have a dipole, for instance, because the star has a dipole and it will create the wind. What you do have is initial conditions that are not exactly the equilibrium, and you look for relaxation towards equilibrium. And I think it's very dangerous to mix what you see, the history of what you see, with something that would be the evolution of the system. Unless you have something that is getting quasi-periodic, so then, okay, once it's getting quasi-periodic, you see that it's the evolution of the system. But your question is really important. Yes, I think at some point you have to analyze what are the instabilities that are created there and why they disappear so easily, maybe also.
Okay, thank you.
Okay. Other questions, comments to Christophe? That's not the case. So let's thank again Christophe for the very nice seminar, and thank you also everybody for joining in. So have a nice evening, everybody.